Welcome to this pre-recording of lecture 40 of MCS 481. So this will be the last pre-recording in this course. We will go to a related problem related to the robot motion planning. We are interested in shortest path and the connection with graphs and finding the shortest path in a graph is made. So this problem of finding a shortest path, avoiding obstacles, translates into a visibility problem. As this is the last lecture, and there might not be, and there most likely is not a final exam, I will nevertheless review very shortly after the material after the second midterm exam. And then at the very end, make a conclusion about what we've done in this course. Okay, so we have in a previous lecture, so lecture 38 to be precise, we have considered robot motion planning via trapezoidal maps. So here is the construction. We have three obstacles. We have a start position, a target position, and the trapezoidal map is refined with vertices on the midpoint of the extensions, of the vertical extensions, and also with the centers of the trapezoidal cells. So this gives a graph where the edges in the graph connect the end points of the trapezoidal cells with the midpoint. So in designing a path, you first locate the start position in which trapezoidal cell does the start position lie. You go to the center, and then also you navigate towards the goal doing a breadth first search or a depth first search of graph algorithms. So here is a concrete example. We've seen that the cost of computing a trapezoidal map is n log n, where n is here the number of obstacles, where these obstacles are polygons with a modest number of vertices. So, and that trapezoidal map, the construction of the trapezoidal map is actually the main cost, so the n log n. Fine, problem solved, but if you would see this in practice, you actually see that this is kind of a crooked path and actually not so satisfactory. So in this lecture, we are interested in finding the shortest path. So again, this is in robot motion planning, but we are only considering a floor plan. So this is in the plane. We are only considering robots that can be reduced to a point. So we are not going to do Minkowski sums, and we're certainly not going to do them in 3 dimensions. As was the topic then also of that other lecture. I don't want to trivialize lecture 38. Okay, so this is the problem statement of lecture 38 with one important modification here colored in red. We want to compute a shortest path for a robot. And again, avoiding the obstacles. Okay, so this is here the problem statement again. 3 obstacles in a bounding box, so I'm recycling the problem data. We have a start position and a target position. Then solving this, if there are no obstacles, this would be just drawing a straight line from start to target. But if you were to do that, you would hit here that obstacle. So you can't really do this. Well, you could say you can kind of twist that, so kind of modify that straight path so that you touch on that vertex here. And the vertex is, you can't see the target if you imagine now, so this is a floor plan, but you could think of these trapezoidal, these obstacles as 3D, so that they have, that the red lines are actually vertical walls. Then from the start position, you can actually not see the target. You have the coordinates of the target, so actually you know that what the path is, and you would bump into this wall here. One alternative would be to navigate, so where you get to this and then go to that vertex. But here you actually see that you could go straight through that vertex. So that's the vertex that you can see. And then from that vertex, once you have turned the corner, at that vertex you can see the target position. So the point of this very simple example is to kind of give the geometric intuition that finding the shortest path is related to determining the visibility of all the obstacles. What vertex can you see? So here is the characterization of the shortest path. So the shortest path will be a collection of line segments and they connect each other, so it's a polygonal path. So we have the beginning and the end, start and the target, and we have inner vertices. Now there are the blue environments, but actually the sentence in between, all inner vertices of a shortest path are vertices of the obstacles. That's the important sentence here on the slide. So straight lines are typically, if you walk in a straight line, you from start to target, that's the best way. But we can't do this. We have these polygonal obstacles. So the statement, the important sentence here, is spelled out in greater detail in the lemma. So the lemma takes on input a set of disjoint polygonal obstacles. We have the coordinates of the start and the target position. And then any shortest path between start and target, no matter where they are, of course, the coordinates should be outside the obstacles. So any shortest path is actually a polygonal path where the inner vertices are vertices of the obstacles. So we're going to prove this lemma. That will be the last proof that we get into in this course. So let's us first stare at this statement of the lemma a little bit longer. So we have to see the important characteristics. So we have a path that consists of line segments, so no crooked lines. So you could think about, can you go in an arc from start to target? Might look a little bit better, but that will not be the shortest path. So that is what we will prove. So it's polygonal, and also that the inner vertices are the vertices of the obstacles. And we will assume that this is not the case. We will assume that there are nice bending curves, and we will also assume that there will be vertex points that are not vertex points of the obstacles. We will prove these statements by contradictions. So this is a geometry course, but actually if you have taken course in analysis, you will recognize the arguments. Okay, our first statement in the lemma is that the shortest path is a collection of line segments. Assume now that you have a curved segment. So you have a segment that is an arc. It's not a line segment. So assume that you have such an arc, and there is a point on this arc. So it is curved. Then you can take a non-empty disk centered at the point, and so the point is on the polygonal path, so it's not touching any of the obstacles. So there is a non-empty disk. So you have an arc somewhere. Well, you see, if you go from the look at the left and the right, so in some sense it is a picture proof that you can replace that arc by a line segment. So the black line segment is obviously shorter. So if you take an arc, you can always take a shortcut. And well, you say, but you know what? That this can be very small, and there are other curves around the non-empty disk. Well, you could repeat that argument. So then where the black line here, suppose that you cannot extend this disk any further, you could actually have vertices that are at the intersection of this curved point and the line segment. So this is an argument that if you have taken a course in analysis might seem quite familiar. It has also a nice geometric picture. So this proves by contradiction, assuming that you have somewhere an arc, that you can replace the arc by a shortcut. And the shortcut is shorter, so the curve, the arc that you had, cannot be on the shortest part. And you can do this construction for any arc. Okay, so the second point is that we have now line segments on our shortest path. But assume now that there would be an inner vertex, so not a target, not the start. So suppose that there would be an inner vertex which is not a vertex of the obstacle. Well, we do the same argument again. So it's again a picture proof. Since it is not a vertex of an obstacle, there is a non-empty disk. Again, from analysis, it could be infinitesimal, but it is not zero. So there is a non-empty disk that has as center that vertex that is now on a polygonal path. But then you see there is again a black line, there is again a shortcut where you can find a shorter path. So that means that the vertex P cannot be a vertex, cannot be an inner vertex in the shortest path. Okay, so this proves the lemma. So we have polygonal paths, and we do have the vertices are the inner vertices. Okay, so here is the example now of the visibility graph. So for every vertex, you draw an edge. If you stand at the vertex, you can see the other vertex. So the connection is the connection, two vertices are connected if they can see each other. So it's an undirected graph, so it's symmetric. So here is the visibility. So this is the definition now of the visibility graph. So because of the lemma, this definition makes sense. So in the context of shortest paths. The vertices are the vertices of the obstacles, and the edges are between the vertices that see each other. So we now have a new data structure that is the visibility graph. And the consequence of the lemma is essentially that the shortest path between a start and a target is actually the collection of edges that contains the vertices of the obstacles, and added to this are two other vertices, the start and the target. Okay, so here is the visibility graph with the start and the target added to it. So when we add the start, we also determine the visibility of that um, start position to all the other vertices. Okay, so here is now the shortest path. So this is the picture we started with. So the blue lines define the search space. So of all the possible routes that we can take, there is at least one, there could be multiple, there is at least a shortest path. So here indicated in black, in the thick black lines. Okay, so then here is the picture of our problem now. It has been reduced to a graph problem. So the obstacles, you can still see the outline. So the edges of the obstacles are still represented. One can follow an edge along an obstacle, jumping from vertex to vertex. Okay, so there has to be an exercise in every lecture. The goal of the exercises, the reason why they are put smack in the middle, is that it is necessary often to reflect a little bit. Knowing the answers of the exercises, so they will no longer be collected, but knowing the answers of the exercises is often necessary to continue. So I said it was a undirected graph. It will of course become directed if we go from start to target. So in some sense you could say what is missing is that you could put a direction to this. So from start you could see this as a source, and the target is the sink. The main thing what I'm after here is the distances. So we always start from a geometric question, so we see which edge is shorter than the other. If it has to be turned into a numerical problem, what is missing from this picture are the distances. So it's important that to observe that this is still an undirected graph. We can go in either direction. Visibility is a commutative operation, but the distances are the weights. So that is what is missing from this picture. And it's a nice picture, so it would mess it up. But so this is actually what is missing. Okay, then we have essentially solved the problem. So here is the method formalized into an algorithm. So we reduce the shortest path for a point robot to finding a shortest path in the visibility graph. So the visibility graph is computed in the first step of this algorithm, where again the vertices of the graph are the vertices of the obstacles, which are convex polygons. There is the start position and the target position that are added. So the output is computed, so here you see what is missing, step 2. So when we have determined the visibility, we are adding the weights. So you could see this as we determine the visibility. We could do this in a separate step, but that is depending on the two steps. And then we have Dijkstra's shortest path algorithm. So this is not a course on graphs algorithms. So the running time of Dijkstra's algorithm is n log n, where m is depending on the number of edges. And the number of edges could be quadratic. So if you have a graph that is, so in some sense, our running example, we had only very few obstacles, and one could see most vertices, there were many connections. In practice, it is of course that there could be many obstacles, and this graph could be quite sparse. What you actually hope in practice is that the number of edges is linear in the number of vertices, or is at most n log n. Okay, so we're still not done here. When we are after efficient algorithms, the computing cost of this visibility graph is now our main problem. And we actually hope that this is also n log n. Okay, one key property is that one key problem in constructing the visibility graph is something that we have not touched. How do you actually have an algorithm to systematically compute the visibility from a point? So here the point, I've took it as the center point. It could be another vertex, it could be the start coordinate or the target position. So if we can do this from any point, then we can do this. So here this picture suggests a first algorithm. So to make sure that we understand the problem, what you can do is from your point, you can consider all the line segments to any other vertex points of the obstacles, and then determine whether these line segments intersect the edges. So in the course we have seen the line segment intersection problem. So in some sense this is a problem that we can solve already, but this viewpoint is mainly intended for understanding the problem. So the problem is any problem that we consider should be well defined. So this point of view is interesting from that perspective. Okay, so we have to say what we mean now, what is visible, intuitive, it is clear. So from the previous picture, we can say that a vertex is visible if the line segment does not intersect any obstacle. And the interior means the interior of the edges. Well, if it intersects, it has to go in and out. The obstacles are convex. Okay, if the problem is indeed already solved if you want only one point. But if you would do that, it would actually be, if you would do this for all the pairs of the vertices, note that, so if you are interested in one point, then there are n vertices here. So for this problem, the n is not the number of obstacles, but the total number of vertices. So then you have to consider every other vertex. There are n vertices, and it is a primitive. So we have the line segment of the vertex point, and then you have to see whether you're intersecting or not. And you can do this by starting in the vertex and actually running around the polygons. And I said that n is the number of vertices, not exactly correct. It will be linear in the number of obstacles. But if you have to do this with all the pairs of vertices, so all the pairs, this is n square, you do n steps, then you have an n to the power 3 algorithm. And that is particularly bad if you're dealing with large graphs of millions of vertices. We can do a lot better, but it still will be a quadratic algorithm, actually a little bit worse than quadratic, n square log n. So in some sense, the bottleneck of the shortest path computation will be the visibility graph. In a way, this is so you can now, in some sense, it is understandable. We have seen that computing a roadmap via trapezoidal maps is n log n. Here, actually, if we want to be a little bit better, we want to have the shortest path, well, we have to allow for an extra overhead, if you like, of a factor n. So it's going to take you n times longer to do. Okay, so how do we go from a cubic algorithm to an n squared log n algorithm? We will do a rotational sweep. So again, we consider one point and then we consider all the obstacles, and we will exploit the fact that the obstacles are represented by their convex hulls. So the obstacles are convex hulls in the plane, which we represent by ordered sequences of vertices. So they're ordered cyclically, either counterclockwise or clockwise. So here is the picture. So we see the red arrows. I opted now for the clockwise order. And you can see that if you go from one visible vertex to the next vertex, that this will help you. So intuitively, the fact that you go from one visible vertex to another may already matter to determine the visibility. Okay, I'm a little bit running out of steam here also at the end of this course. And this is also a good opportunity to actually ask for an extra exercise. Think about this, how this could be formalized. So think about this on how you would organize this rotational sweep and how this would be more efficient than the plain algorithm that considers all the vertices independently. So now the vertices are part of this convex hull. Okay, after solving this exercise, I should mention the conclusions. So as far as this lecture 40 goes, I'm at the end almost. So summarizing, with the trapezoidal map, we could solve the road map problem for a point robot in n log n time. If you want to do a little bit better, you want the shortest path, you can do this in n square log n time. I'm not proving this theorem either. This is at the end of the course. Please look at the textbook. In some sense, this is still the goal of this course. The textbook is very extensive. One of the goals of this course is that you find your way into the literature. Okay, so to conclude the lecture, I should point at the user manual of Sigal, which has a package to solve the visibility problem in the plane. And here you see the examples. So again, if you are a good programmer, you could do this yourself. But the advantage is that, so even if you do this yourself, please look at the documentation, that you kind of are aware of the pitfalls and the assumptions that you will have to make. So here you can see that this is done in a greater uh, generality. So there is the regularity of the problem. There are several algorithms for this. So here you see the computation of the visibility. So in a way, uh, we make the connection with robot motion planning, but this is also very important in computer graphics. If you would walk through a scene, which data structures would you be using? Running time in practice. So you see this n square log n factor. So that this can still be solved extremely quickly. And there is always code attached to this as well. So we have polygons that may have holes in there, where this is another topic. Okay, this concludes the lecture on visibility graphs. So I'm about more than halfway in. I'm still gonna spend about 10 minutes to review the materials that we have considered after the second midterm. So after the second midterm, we studied convex hulls in 3 dimensions. And then I had topics for covered that, so the convex hull in 3 dimensions was covered in chapter 11, and then we've gone through chapters 12, 13, 14, and now 15. So I will not show a picture for this lecture, so there are plenty of pictures. But I will try to recapitulate the essence. So graphs are very important data structures. Any convex polygon in 3 space corresponds to a planar graph, and we have used this construction together with Euler's theorem to say something very important about the complexity. So very importantly, so convex hulls in 3 space look already very complicated objects. There can be many facets, but the complexity is linear in the number of vertices. The number of edges, the number of facets, it's linear in the complexity. So the viewpoint of taking a planar graph, but by the way, we did not, so that was an important problem in geometry. So this is computational geometry. In every lecture we try to prove something, but still we are unfortunately not completely self-contained. So the theorem that for every convex polygon there is a planar graph, so the graph is planar, that is an important theorem which we kind of skipped. Okay, so what is important in this course are algorithms. So we defined the horizon, again related to what we have covered before already, the visibility graph. So if we work on an incremental construction of the convex hull in 3 space, we add a point and we have to replace all the facets that we see from that point. So here in this picture, kind of a schematic, we have the green plane that passes through the top facet. What is visible are the blue edges, and they will be replaced. So I'm sorry, so the facets, that a span will be replaced. The edges will be the edges in the triangles which have as extra vertex the new point. So this was kind of the idea for an incremental in construction of a three-dimensional convex hull. Visibility, again, it connects to what we have covered today. So then in the third lecture, we made the important connection between three-dimensional convex hulls and Voronoi diagrams. And we already knew that Voronoi diagrams are their dual defines the Delaunay graph, which can be used to compute the Delaunay triangulation. And this was very important when we looked at the spatial module of SciPy, which wraps QHull, quick hull. So again, the important thing of this lecture was also that we have shown one part of the n log n result, that a randomized incremental algorithm will work in n log n time. So this is the picture of that third lecture on convex hulls in tree space. So we spent 3 lectures on the convex hulls in tree space, which allowed us to give a little bit broader, a little bit deeper into this subject. Again, the subject is justifying a lot more than just what we could cover in this course. Okay, so then we have the binary space partitions, also related to visibility. So if we want to render a scene, we have to determine which objects we have to hide. So we were trying to implement the painter's algorithm. So if we have a blue sky, green grass, green trees, and then a red house, we first paint the blue sky, then the green tree, and then the red house. So that was the cartoonish description. Here you see one of the slides of that lecture where we define a tree, so it's the binary space partition tree, where the objects, or at least the fragments of the objects, are stored in the leaves. And then we use this tree, we traverse the tree, we locate the viewpoint in one of the regions that is represented. So we have the lines at the nodes of the tree that were used to split the objects, led to fragmentation. We first, so there's the convention right and left, whether we can see it or not. So again, visibility played an important role here. We studied the problem only in the plane. So it has a nice extension in space. Okay, then we had the robot motion planning. So I referred to this at the very beginning in the lecture. So this was for point robots, for robots that cannot be simplified to a point. We have to compute the Minkowski sum. So here you see in blue the robot with its barycenter at the origin and then an obstacle. Now if you compute the sum, so you flip the robot, so this is where the minus comes in, the sum is called the Minkowski sum. Then you see that in blue, the blue line goes to the barycenter. that in this blue you recognize the edges of the obstacle, and you also recognize the edges that are parallel to the robot. So actually the blue envelope kind of stores the information of the obstacle and the robot. As you can see, for if everything is in general position, that the number of edges in the blue envelope is the number of edges in the obstacle and the number of edges in the robot. So that was a very important complexity result, because then computing the Minkowski sum in the plane can be done in linear time. It's like doing the merge step in a merge sort. Very attractive. Um, in tree space, life gets a lot harder. So there actually I pointed to the Seagal documentation, where you have a more than cubic. So you have a cubic in the number of vertices, in the number of vertices and edges, and the complexity of the robot, and then times a cubic factor in the obstacles. Okay, in the previous lectures we discussed the generation of meshes, and we had a very simple data structures, the Quadtree. Here you see the defining structure of the Quadtree, where we are storing points, we're putting actually the points into boxes, into squares, recursively subdividing. If we have a point collection, we compute the center, the middle coordinates, and we use that to split. It's a Quadtree for the quadrants in the plane, the 4 quadrants, and every Quadtree has 4 children. And it is a recursive data structure. Triangulating the squares leads to leads to a triangulation where all the angles are either 45 degrees or 90 degrees. So that's another way to actually construct triangulations. Quadtrees have advantages because of their simplicity. They also have disadvantages. We did not discuss the generalization to 3 dimensions, but in 3 dimensions we have octant. Then we have octtrees, trees with 8 children. Okay, so I come to the conclusion now. So this is my last pre-recording, also will be my last lecture, as we will go into project presentations. So here again, a definition of computational geometry where we solve geometric problems. Computational geometry is motivated by applications, and making the link between the data structures and the algorithms is the software. So in this course, it's between mathematics and computer science. So we try to be very precise in defining what we were doing, what was the problem, what was the complexity, and describing this in the proper language of mathematics. In the computer science aspects, this is actually a second data structures course where we are storing numerical information that has a geometrical interpretation. Very useful for database queries. Our algorithms tend to be quasi-linear n log n. These are the most efficient algorithms related to sorting. But often, and more than often, certainly if we go to 3-dimensional space and if we are considering highly degenerate or special configurations, that is not possible. Okay, so this is the conclusion of this course. I hope this sequence of lectures was interesting.